Welcome back to Lesson 15 in our discussion of the transport layer of the TCP/IP model. What we've been discussing in the last two lessons has been the problem of congestion control in the transport layer. So let's continue with scenario number 3. In our final congestion scenario, 4 hosts transmit packets, each overlapping 2 hop paths. We again assume that each host uses a timeout retransmission mechanism to implement a reliable data transfer service, that all hosts have the same value for input speed, and that all router links have the same capacity R. Let's consider the connection from host A to C, as you see here, passing through routers 1 and 2. The A to C connection shares router 1 with the DB connection and shares router 2 with the BD connection. For the remainder of this discussion, we'll remember that AN, application N, is the amount of data being passed down from the application. For extremely small values of AN, buffer overflows are very rare, and the throughput approximately equals the offered load. Now you remember offered load was that TN value, which was the data being passed by the transport layer to the network. For slightly larger values of AN, the corresponding throughput is also larger, since more original data is being transmitted into the network and delivered to the destination. Overflows are still rare. For small values of AN, an increase in AN results in an increase in TN, obviously. Having considered the case of extremely low traffic, let's next examine the case that AN, and therefore TN, is extremely large. TN, transport N, you recall, is the amount of data being passed from the transport layer to the network. This is after it's added its own header information to the data that was passed down by the application. Consider router 2 right here. The AC traffic arriving to router R2, which arrives at R2 after being forwarded from R1, can have an arrival rate at R2 that is at most capacity, or R, the capacity of the link from R1 to R2 regardless of the value of AN. If AN is extremely large for all connections, including the B to D connection, then the arrival rate of B to D traffic at R2 can be much larger than that of the A to C traffic. Because the A to C traffic and the B to D traffic must compete at router 2 for the limited amount of buffer space, the amount of AC traffic that successfully gets through R2 that is not lost due to buffer overflow becomes smaller and smaller as the offered load from BD gets larger and larger. Why is that the case? Because there is not a router R1 between B and R2. And there is another router between A and R2, which slows A's down. Therefore, B traffic will hit the router R2 first. Remember, the offered load is the amount of data being passed from the transport layer, TN. As the offered load approaches infinity, an empty buffer at R2 is immediately filled by the BD packets, and the throughput of A to C connection at R2 goes to 0. This in turn implies that the A to C end-to-end throughput goes to 0 in the limit of heavy traffic. The reason for the eventual decrease in throughput with increasing offered load is evident when one considers the amount of wasted work done by the network. In the high traffic scenario, whenever a packet is dropped at the second hop router, the work done by the first hop router in forwarding a packet to the second hop router ends up being wasted. The network would have been just as well off if the first router had simply discarded the packet and remained idle. More to the point, the transmission capacity used at the first router to forward the packet to the second router could have been much more profitably used to transmit a different packet. So here we see yet another cost of dropping a packet due to congestion. When a packet is dropped along a path, the transmission capacity that was used at each of the upstream links to forward that packet to the point at which it is dropped ends up having been wasted. Here we identify the two broad approaches to congestion control that are taken in practice and discuss specific network architectures and congestion control protocols using these approaches. We can distinguish among congestion control approaches by whether the network layer provides any explicit assistance to the transport layer for congestion control purposes. In an end-to-end approach to congestion control, the network layer provides no explicit support to the transport layer for congestion control purposes. Even the presence of congestion in the network must be inferred by the end systems based only on observed network behavior. We'll soon see that TCP, the transport layer, can necessarily take this end-to-end approach toward congestion control, since the IP layer, that is the network layer, provides no feedback to the end systems regarding network congestion. TCP segment loss is indicated by a timeout, or a triple duplicate acknowledgement is taken as an indication of network congestion, and TCP decreases its window size accordingly. We will also see a more recent proposal for TCP congestion control that uses increasing round-trip delay values as indicators of increased network congestion. On the other hand, with network-assisted congestion control, network layer components, that is routers, provide explicit feedback to the sender regarding the congestion state in the network. This feedback may be as simple as a single bit indicating congestion at the link. More sophisticated network feedback is also possible. For example, one form of congestion control allows a router to inform the sender explicitly of the transmission rate it can support on an outgoing link. One protocol provides router computed feedback to each source carried in the packet header regarding how that source should increase or decrease its transmission rate. For network-assisted congestion control, congestion information is typically fed back from the network to the sender in one of two ways. Direct feedback may be sent from the network router to the sender. This form of notification typically takes the form of a choke packet, essentially saying, "I'm congested." This second form of notification occurs when a router marks or updates a field in a packet flowing from sender to receiver to indicate congestion. Upon receipt of a marked packet, the receiver then notifies the sender of the congestion indication. Note that this latter form of notification takes at least a full round-trip time. As we have already discussed, TCP provides a reliable transport service between two processes running on different hosts. Another key component of TCP is its congestion control mechanism. As we have just learned, TCP must use end-to-end congestion control rather than network-assisted congestion control, since the IP layer provides no explicit feedback to the end systems regarding network congestion. The approach taken by TCP is to have each sender limit the rate at which it sends traffic into the connection as a function of network congestion. If a TCP sender perceives that there is little congestion on the path between itself and the destination, then the TCP sender increases its send rate. If the sender perceives that there is congestion along the path, then the sender reduces its rate. But this approach raises three questions. First, how does a TCP sender limit the rate at which it sends traffic into the connection? Second, how does a TCP sender perceive that there is congestion on the path between itself and the destination? And third, what algorithm should the sender use to change its send rate as a function of perceived end-to-end congestion? Let's first examine how a TCP sender limits the rate at which it sends traffic into the connection. Previously, we saw that each side of the TCP connection consists of a receive buffer, a send buffer, and several variables. Last byte read, you recall, RWND, and so on. The TCP congestion control mechanism operating at the sender keeps track of an additional variable, the congestion window. The congestion window, denoted by CWND, imposes a constraint on the rate at which the TCP sender can send traffic into the network. Specifically, the amount of unacknowledged data at a sender may not exceed the minimum of CWND or RWND, that's the receive window. In order to focus on congestion control, from now on let's assume that the TCP receive buffer is so large that the receive window constraint can be ignored. Thus, the amount of unacknowledged data at the sender is limited by CWND. We'll also assume that the sender always has data to send. In other words, that all the segments in the congestion window are sent. The constraint that we have just defined limits the amount of unacknowledged data at the sender and therefore indirectly limits the sender's send rate. To see this, consider a connection for which loss and packet transmission delays are negligible. Then, roughly, at the beginning of every round-trip time, the constraint permits the sender to send CWND bytes of data into the connection. At the end of the round-trip time, the sender receives acknowledgements for the data. Therefore, the sender's send rate is roughly the congestion CWND divided by round-trip time, or RTT. That's in bytes per second. By adjusting the value of CWND, the sender can adjust the rate at which it sends data into the connection. Let's next consider how a TCP sender perceives that there is congestion on the path between itself and the destination. Let's define a loss event at a TCP sender as the occurrence of either a timeout or the receipt of 3 duplicate acknowledgements from the receiver. Recall from our discussion earlier of the timeout event and the subsequent modification to include fast retransmit on receipt of 3 duplicate acts. When there is excessive congestion, then one or more router buffers along the path overflows, causing a datagram containing a TCP segment to be dropped. The dropped datagram, in turn, results in a loss event at the sender, either due to a timeout or the receipt of 3 duplicate acknowledgements, which is taken by the sender to be an indication of congestion on the sender-to-receiver path. Remember now, the acknowledgement contains the next sequence number that the receiver is expecting. Including the same sequence number in all 3 acknowledgements logically suggests that the datagram with that number was lost. Now that we have considered how congestion is detected, Let's next consider the more optimistic case when the network is congestion-free. That is, when a loss event does not occur. In this case, acknowledgments for previously unacknowledged segments will be received at the TCP sender. As we'll see, TCP will take the arrival of these acknowledgments as an indication that all is well, and will use acknowledgments to increase its congestion window size, resulting in an increase in its transmission rate. Note that if the acknowledgments arrive at a relatively slow rate, then the congestion window will be increased at a relatively slow rate also. On the other hand, if acknowledgments arrive at a higher rate, then the congestion window will be increased more quickly. Because TCP uses acknowledgments to trigger its increase in congestion window size, TCP is said to be self-clocking. Given the mechanism of adjusting the value of CWND to control the sending rate, the critical question remains: how should a TCP sender determine the rate at which it should send? If TCP senders collectively send too fast, they can congest the network, leading to a type of congestion collapse. However, if TCP senders are too cautious and send too slowly, they could underutilize the bandwidth in the network. In other words, the TCP senders could send at a higher rate without congesting the network. How then do the TCP senders determine their sending rates such that they don't congest the network, but at the same time make use of all the available bandwidth? Are TCP senders explicitly coordinated? Or is there a distributed approach in which the TCP senders can set their sending rates based only on local information? TCP answers these questions using the following guiding principles. A lost segment implies congestion, and therefore the TCP sender's rate should be decreased when a segment is lost. Remember that a timeout event, or the receipt of 4 acknowledgments for a given segment, 1 acknowledgment and then 3 duplicate acknowledgments, is interpreted as an implicit loss event indication of the segment following the 4 acknowledged segments, triggering a retransmission of a lost segment. From a congestion control standpoint, the question is how the TCP sender should decrease its congestion window size, and by extension, its sending rate, in response to this inferred loss event. An acknowledged segment indicates that the network is delivering the sender's segments to the receiver, and therefore the sender's rate can be increased when an acknowledgment arrives for a previously unacknowledged segment. The arrival of acknowledgments is taken as an implicit indication that all is well and the network is not congested. The congestion window size can be increased. Given acknowledgments indicating a congestion-free source to destination path and loss events indicating a congested path, TCP's strategy for adjusting its transmission rate is to increase its rate in response to arriving acknowledgments until a loss event occurs, at which point the transmission rate is decreased. The TCP sender increases its transmission rate to probe for the rate at which congestion onset begins, backs off from that rate, and then begins probing again to see if congestion rate has changed. Note that there is no explicit signaling of congestion state by the network. Acknowledgments and loss events serve as implicit signals. Each TCP sender acts on local information asynchronously from other TCP senders. Given this overview of TCP congestion control, we're now in a position to consider the details of the TCP Congestion Control algorithm.